Hi, we are Group 14 of EC 504. Our project is called Bouncing Shape. The objective of the project is to create a program that can perform physics simulation of 3D figure which consists of at least 1 million triangles, and those triangles are not necessarily connected. The figure will also interact with the simulation boundary and experience some certain deformation during collision. Note that the required input is actually a triangle mesh, which is a concept in computer graphics. The relevant background information for this project is to understand that we are given two objects. A 100 by 100 by 100 3D cube is the boundary to our game world and a 3D triangle mesh grid. The goal that we want to achieve is to simulate a system with those two objects with a frame per second of 1 or more. The key elements to this project are a triangle mesh, 3D collision detection, physics engine, and Java graphics. For our project we had two major choices we had to make early. We had to choose how to implement our physics engine and how to implement the Java graphics. When implementing the physics engine, we had two options: Verlet integration or rigid body dynamics. Due to convergence issues we chose rigid body dynamics. When implementing the Java graphics we had two options: Java FX and JMonkeyEngine. JMonkeyEngine had flexibility in UI, shading and texture, so we chose that option. The process of our design is represented in this diagram, which includes the data structures used in the program. To initialize our system, we want to center the figure towards the environment. After this we set up the environment for our physics engine by creating 3x3 transform matrices which will be used later to project each vertex to their actual locations frame by frame. To initialize the input mesh, we used a hashmap to help with input parsing, making the overall time complexity from big O n squared to big O n. We implement this by finding identical points in the input and marking them as the same point in the data structure. The main loop for our project is represented in this diagram. The physics engine will update the momentum of the input shape based on the force given by the collision detector. It will also update two data structures: the 8 points in the bounding box and the current location of each vertices. The two structures will be used as collision detections. Physics engine will calculate the transform matrix based on the object's momentum. Then, it will use this matrix to update the two structures. This process requires big O n time. The transform matrix can express 3D shift, 3D rotation, and 3D deformation. In theory, this process can be parallelized by GPU. The way that we designed the collision detection is first by implementing an AABB tree. The AABB tree will have nodes that contain 3D bounds. Each node will have maximum of 2 children. The children can either be a leaf or a bound. The leaf nodes will have no children. The leaves will be at the bottom of the tree, and its parents will be the bounds that encompass the bounds of its children. The collision detection will start at the root node, and traverse down the tree, to see if there is a possible collide with a fixed object. It will do this by checking if the 3D bounds of the triangle object are inside the 3D bounds of the current node. Once it detects a possibility, it checks each vertex in the triangle object to see if it collides with the minimum and maximum x, y, z parameters of the fixed object. In our working implementation we simply check to see if the vertices of the triangle object exceed the bounding box for all objects. We choose JME for the display part. It's a 3D graphics engine based on scene graph. Every JME application has a root node, and elements of the scene graph are spatials, which are attached to the root node as children nodes. UV mapping is used to apply texture. Basically it projects a 2D image to the 3D model surface. The shading can be easily applied by JME, given the figure's vertex normals. An HUD overlay is added to show real-time velocity. Velocity manipulating and mouse response are implemented, after defining key mappings and triggers. In terms of the feature innovations, one thing we want to mention is the input and testing. We introduced STL file parser, because under the hood, STL stores triangles, as shown on the right. STL can be exported from major modeling software. We make use of SolidWorks, thanks to the license from engineering, and some online models to generate the triangles. In order to make sure the two parsers are identical to output the same expected data structure, we make use of unit tests. Also we introduced headless system tests to automatically test if the metric of frames per second is above 1. Another feature we implemented is a Zen game. Sometime in life we forget to enjoy the little things. The target is simple. Click the mouse to interact with the movement of your favorite shape in a subtle way. Ease up your mind from the stresses of your daily life with simply clicks. We would our interactions with the shape to be extremely addiction, so we decided to share our joy with everyone else. Now, demo time. First thing we want to mention is that the cute banana you are seeing now consists of 1 million triangles, which is how most of the computer graphics work currently. However, the FPS is still as high as 70. We got some reviews that the shading and deformation are not clear. Looking at the figure now, you may wonder this as well. Let's start with removing the shading, and replacing the texture with green color, by modifying the code. You will notice the darkness. To compare, add the shading to the figure. You will notice the different brightness on different area of the figure, which is what we consider as shading. As for the deformation, we admit that due to how we apply the physics to the model, the deformation effect cannot be that exaggerated. However, look at this comparison of bouncing on the ground, with strength argument 0 and 100, which shows how the deformation is tunable. Velocity and gravity can all be adjusted in 3 coordinates. What is showing now is the 3D gravity, pointing to the corner of the space. Last thing we want to show you is the ability of adjusting viewpoint, thanks to JME Engine's Flycam component. Thank you for listening to our presentations.